final speaker for this evening is going to be Michael from the California University of Pennsylvania.
Hello everyone, I'm Michael from California University of Pennsylvania, and what I'm here to talk about is one of the proofs me and Natalie Hilbert, my partner, we approved, and it was mainly focused on Fibonacci. So first I'll cover what is going to be going on there. So first we'll talk about the preliminaries, which is what the Fibonacci numbers are, why they are so important, and the Fibonacci association and quarterly that we got our proof from. Then we'll look into the first problem itself, and then look at some of the theorems and identities that are in the handout that I gave you that we use to help us solve the proof and then the proof itself. And then in conclusion, we'll talk about what's going on now and then the future endeavors. First thing I'll talk about is the Fibonacci sequence. It's wherever it starts off with 1 and 1, and then you add the two previous numbers to get the next number in the sequence. So do 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and so on, and it goes on. So we can generalize the Fibonacci sequence as f sub 1 is equal to 1, f sub 2 is equal to 1, and f sub n is equal to f sub n minus 1 plus f sub n minus 2 for every n greater than or equal to 3. And you may ask why Fibonacci is so important. Well, we can see it in nature with the number of petals on flowers. Like in the first picture, we have the flower has 3, which is in the sequence. We also have 5, 13, and 8 in the other pictures of flowers. So we can see that Fibonacci appears in the petals of flowers. It also appears in the pairs of rabbits that are produced each month. In the first month, we'll have 1 pair of rabbits, and then the second month, we'll have another 1. And then the third month, we'll have 2, and then we'll have 3, and then we'll have 5. And this continues on with the Fibonacci sequence. And also, it can be appeared in biology, combinatorics, formal languages, and many other things. So the Fibonacci association was incorporated in 1963 and focuses on Fibonacci numbers and related mathematics, emphasizing new results, research proposals, challenging problems, and new proofs of old ideas. And this is the website, whenever you log on to it, that you will see with the Fibonacci association. Then the Fibonacci association created the Fibonacci quarterly, which is where mathematicians and professionals can submit ideas and problems in there. And also, like with these, you can also, undergrads can also be able to solve these, not just for professionals and mathematicians. And also, they want to make sure like it's a well-developed list of references. So this is a problem that we solved in the May 2013 issue. So we wanted to prove that let n be a positive integer, prove that 1 over n times the nth root of the product from I equals 1 to n of 1 plus f sub n times f sub n plus 1 over f sub I squared is greater than or equal to 1 plus the nth root of the product from I equals 1 to n of f sub I squared over f sub n times f sub n plus 1. So one of the first useful theorems that we found was Müller's inequality, which is where we let x sub 1, x sub 2, all the way up to x sub n, and y sub 1, y sub 2, all the way up to y sub n be positive real numbers. Then we would have the nth root of the product from k equals 1 to n of x sub k plus y sub k is greater than or equal to the nth root of the product from k equals 1 to n of x sub k plus the nth root of the product from k equals 1 to n of y sub k. Another important theory we used was the inequality of arithmetic and geometric means, or known as AMGM. And we would let x sub 1, x sub 2, all the way up to x sub n be non-negative real numbers. And then for the first part of it, we would say the nth root of the product from k equals 1 to n of x sub k is less than or equal to 1 over n times the summation from k equals 1 to n of x sub k. And then also the second part is the nth root of the product k from k equals 1 to n of k sub x is greater than or equal to n over the summation from k equals 1 to n of the inverse of x sub k, if x sub k does not equal 0 for all k of 1 all the way up to n. Then also we use the Fibonacci identity, which is just, it would be the summation from k equals 1 to n of f sub k squared is equal to f of n times f of n plus 1. So now we're back to the original proof, and then our next step was we were proving that 1 over n times the nth root, the product of from I equals 1 to n of 1 plus fn times fn plus 1 over fi squared is greater than or equal to 1 plus 1 over n, which is greater than or equal to 1 plus the nth root from the product of I equals 1 to n of fi squared over fn times fn plus 1. So the first thing we used was the Miller's inequality to show that it was going to be 1 over n, and we took the first part of the inequality that we had originally, and we used Miller's inequality to say 1 over n times the nth root of the product from I equals 1 to n plus 1, because we know that anytime we have a product of anything with 1 is always going to be 1, plus the nth root of the product from I equals 1 to n of fn times fn plus 1 over fi squared. And then using the second part of the AMGM theorem, we said then that 1 over n times 1 plus n over the summation from I equals 1 to n of fn times fn plus 1 over fi squared inverse would be the same. And then we figured out that that would be equal to 1 over n plus 1 over n times 1 plus n over the summation of I equals 1 to n of fi squared plus fn times fn plus 1. So then going from there, we just simplify further because we knew that the summation of, we can then separate the summation of f sub I squared. So that's why we moved it out front, and then we just used the Fibonacci identity since we found out that the summation of fi squared is just fn times fn plus 1. So that's what we did there. And then whenever we simplify that, we'll find out that was going to be 1 over n times 1 plus n over 1, which is just equaling 1 over n plus 1, which is what we wanted to prove for the first part. Now we're proving the second part of the inequality. Then we use the first part of the AMGM theorem to say that 1 plus 1 over n times the summation from I equals 1 to n of fi squared over fn times fn plus 1. And then since we knew that f sub I squared was the summation of it, then we just brought it outside, and then we used the Fibonacci identity again, and then we end up finding out that that would be equal to 1 plus 1 over n. So that proves our result. So what now? We submitted this in November 2013, and it's currently under review. And it's anonymously reviewed by professionals in mathematics. And one original proof we highlighted, and every correct solution to the proof will also be mentioned if yours happens not to be the one that it gets highlighted. So, and it's going to be published in May 2014. We're hoping to see ours in there. We're hoping. And then we plan on submitting more proofs later on in the Fibonacci report. Thank you.
We have about 8 minutes for any questions that anyone has.
Could I see the problem you?
Yeah, I have it right here. Like, if you want one, you can come up and get a copy.
Okay, but I meant on the screen.
Which one would you like to see?
Well, what you proved, the question you answered. So you used the AGM. I'm just curious here. So with the AGM, we get, if we have equality, we have special property. The things we're averaging are equal.
Mm-hmm.
Do you know, did you consider if anything like that happens here? If we get equality, does it say something special? Well, I guess that wouldn't make any sense. Yeah, I just, nice work. I probably violated all proper form. I was just curious. That's, anytime I see an inequality, I want to know if something special happens with it, with the equality. I was just curious if you thought about it. You've done a great job.
I honestly didn't really think about it.
That's fine. Yeah, okay.
I think what happens is, in this case, if you go further to what you prove, go a little bit further
Yeah.
to what you actually prove, that 1 plus 1 over n is between those two.
So the middle inequalities are strict?
Yeah,
Okay.
If that will be true, then 1 plus 1 over n will be equal to all
That's
of that.
true.
Yeah.
Okay.
So he actually proved something a little bit stronger than the
Right.
inequality.
What was stated.
Yeah.
Okay.
Mhm.
Thank you.
Just a question, like, why are you interested in Fibonacci sequence and why did you decide to do like this proof and stuff?
Because like, it was kind of interesting because I really never learned about Fibonacci really ever. I kind of wanted to like see what other kind of math was out there for me to like to maybe even like understand. And so that I found the research group at my university, and I was kind of interested in it. I figured might as well give it a try.
Just because you had mentioned some of the occurrences of Fibonacci and a lot of the things we're familiar with, but you also mentioned formal languages. Do you know what those refer to? Not a language, but the occurrence of Fibonacci.
Not really. I mean,
Just syllables.
So just syllables?
Yeah, like the number of syllables in the words is the number in the Fibonacci sequence.
Okay.
It's like they showed examples of it in like Spanish. It's seen in there. So.
All right, if that's it, then let's thank our speaker again.